Good. Okay, welcome everyone. Thank you for joining us in this last seminar of CSE for this semester. So today it's a pleasure to introduce one of our own, John Marshall. So he's a professor of oceanography here at MIT. So he got his PhD in Imperial College, where he then spent some time as a postdoc and as a lecturer until he later joined MIT in 1993. So he's interested mostly in ocean dynamics and also the relationship between the different scales through convection from the mesoscale to very large scales, also climate dynamics and how that affects the planet, and climate modeling through numerical simulation. And I think that today you are going to talk about icy moons. So just go ahead. Just before we start, if you are online and you have any in Zoom and you have any questions, we will take questions at the end of the seminar. Then just write them on the chat, they will read them, or you can unmute yourself. So with any further ado, please go ahead.
Well, thanks very much for inviting me over to talk. I'm going to discuss the ocean circulation on icy moons, and in particular Europa, which is a moon of Jupiter, and Enceladus, which is a moon of Saturn. Now, we think these are deep oceans covered with thick ice. The ocean might be 100 kilometers deep with a 10-kilometer thickness of ice. And what we're seeing is just an image of the surface of the ice. And they are energized. These oceans exist and are energized by tidal heating. And they're of great interest, mainly because they could harbor life. So you could imagine that you've got rock and heat and water, and maybe conditions for life. And there are missions planned to fly to Europa, for example, to look for biosignatures to see whether this is indeed true. And we know something about these moons, but of course we can't probe their interior very well, and so we are trying to figure out what might their ocean circulations look like and why. And we're going to use insights from Earth's ocean, which we know a lot about, and along with fragmentary observations, which I will briefly review, to learn about the circulation. One of the main things people are interested in is if there's hydrothermal activity at the bottom of one of these oceans, what's the transit time between the bottom of the ocean and the ice surface, where we might be able to take some observations. And we're going to develop numerical analogues, and I think that's why one of the reasons this might be of interest to this computational group. So I'm going to focus on Enceladus, which is an icy moon of Saturn. And the reason is that, curiously, we know it's thought that we know more about it than Europa. So Enceladus, it's a moon of Saturn. It's small, only 250 kilometers in radius. And we think there's an ocean underneath it, underneath this thick ice shell. Now, the reason people are pretty confident about this is that Enceladus is in this elliptical orbit around Saturn, but it's in a resonance with Dione, which is another moon of Saturn. And so it kind of wobbles around, and there's a libration going on. And if this were a solid body, then its libration amplitude would be much smaller than if there were an ocean underneath it. You can imagine it being torqued. And if there's a fluid underneath, then the libration amplitude would be larger. So it's from measurements of gravity, libration, and just the shape of Enceladus that people are figuring out that there's an ocean underneath and that there are variations in ice thickness. It's incredibly small. It's about the size of Texas, 250 kilometers, or France or something. And it's in a tidally locked orbit, so it's rotating, and it's got a gravity which is 1/100th of the size of Earth. Now, one of the most important things to appreciate is this concept of the eccentricity tide. So the Enceladus is in this elliptical orbit, and it's getting pulled towards Saturn. And when it's being stretched in the direction of the tidal axis here. And as it gets stretched, that flexing leads to heating. And if you imagine you get a squash ball and you keep squashing it at the top, the squash ball gets hot at the top relative to the sides. So we think that the tidal heating is polar amplified. And so you've got a system where most of the heating is going in at the poles. And one of the lovely things about Enceladus is that there are actually geysers over the South Pole. So you can see water issuing from the ocean through these geysers and sublimating, and you get a great big snowball of it's a lovely thing. And moreover, the Cassini mission flew a device through the little plumes, and from that there was a detection of the presence of silica, organic matter, hydrogen, kind of a slightly alkaline environment in the South Pole of over the South Pole of Giza. So this is all suggestive of hydrothermal activity, and people have thought about the transit times that they can. I should have said this, that it's an interesting thing that the E-ring of Saturn, one of those rings that you can see, it is made up of little silica nanoparticles, which they think largely came from Enceladus spewing water out from and little ice crystals out from the bottom. So this may suggest that there is some tidal, there is some hydrothermal, where's my pointer, some hydrothermal activity at the base, or we don't know, obviously. There's another thing that we have more knowledge of with regard to Enceladus, and this is work that Tushar Mittal did with Hemingway. Tushar was a postdoc working with us until recently. I'll mention Tushar again in a moment. And so from measurements of the topography of Enceladus and its gravitational field, people have surmised that the ice is actually a little bit thicker over the equator than over the pole. So that the ice thickness might be 20 kilometers at the equator and somewhat smaller over the poles. And obviously over the South Pole, it could vanish, and there are cracks in these so-called tiger stripes where you see these stripes of convection occurring over the South Pole. Now this is a map of the ice shell thickness. This is the equator, 30 kilometers in thickness, and at the poles shallower. So these are based on measurements of mean density, moment of inertia, libration, amplitude, surface topography, etc.
We know something about the inner core. Is it considered to be rock, and is it permeable, means water gets change with the core, or we can think about the solid matter in the bottom of the
I don't know much about this personally. I think it's thought to be a silica solid core, which is undergoing some kind of convection in the core, with possibly some hydrothermal activity. People have built models of these processes. We don't know much about the rheology of the ice or the core. We can make estimates of the amount of heat being generated in this system. So if you accept that we know something about the ice thickness, we can compute the surface, that we can compute the temperature at the surface of the moon by just doing an energy balance. So you've got some incoming incoming radiation. You've got sigma T to the 4 going out. You know something about the albedo. So you can figure out what the temperature at the surface is. It's very cold. Now we know the temperature. If we know the ice thickness, then we know the temperature of the water at freezing. And if we know the thickness, then you can invent a diffusive law. If you know the diffusive flux through the ice and you know the temperature difference, you can get the heat flux coming out. And we think it's about 20, 30 gigawatts of heat. This is fairly well constrained. So the ongoing debates are, is the heat primarily generated in the ice shell or in the rocky core? So this tidal heating could be occurring in the core, could be occurring in the ice shell. People don't know about this partition between one and the other. That's because we don't know much about the rheology of the ice or what's going on in the core. Another big uncertainty is how salty is the ocean. As I will mention later on, how salty the ocean is actually matters quite a bit in terms of figuring out what's going on, because it affects the equation of state of water, and whether, if you had heat to the water, whether it gets buoyant or denser. And another thing is, what are the timescales of particle transport from the core to the surface? So if you hypothesize that we've got hydrothermal activity generating 20, which is issuing out in an integral sense of 20 gigawatts of heat into the bottom of the ocean, if that generates circulation, how long is it going to take for a particle to go from the bottom to the top? The geochemists have got some estimates based on assumptions that on Cassini measurements when they flew through the geysers over the South Pole. So this is a collaborative effort. It's in a fairly large project exploring ocean worlds. The PI of the project is Chris German, who is a scientist down in Woods Hole Oceanographic Institution. The MIT and Woods Hole has a close collaboration in the graduate education program. And there are groups looking at the geodynamics, the studying hydrothermal activity, biogeochemical signatures, and ocean circulation. And I'm thinking about we at MIT are thinking about the ocean circulation part. Chris German knows an awful lot about hydrothermal activity on Earth. Of course, as you know, probably know that that's a source of life which is probably distinct from the photosynthetic life at the surface of the surface of Earth's ocean. So in the ocean circulation project, I'm collaborating with Andreas Thurner from Lamont at Columbia University, Christophe Sotin, who used to be at JPL, who's now gone home to France, myself, and there's a kind of EAPS icy moon team. Many of the calculations I'm going to show you today were carried out by Suyash Bire, who's a postdoc working with us. Wang Ying Kang was a postdoc, but now is an assistant professor here in EAPS. Tushar Mittal, I mentioned, he's now an assistant professor at Penn State. He knows about the geophysics of and some of the geochemistry of these moons. There's a research scientist, Jean-Michel Campan, who advises on the modeling. And then there are some grad students. Ali Ramadan, who's a grad student in the computational program here. PJ Tuckman, PJ over there, and Yijiao Zhang. And we've been working with the Europa, Anika Nath here, who's been, I'll show you some of the work that she's been doing with Suyash in a moment, a bit later. So there's a lot of people, lots of papers being written. It's a good field to be in because we don't know much about it. This is an artist's impression of the circulation on an icy moon, and we're trying to kind of, in a sense, overturn this artist's impression. So let's imagine that you've got this rocky core with some hydrothermal circulation and some recirculating water which is heating up, and then out of from these hydrothermal vents issue these jets of buoyant fluid coming up from below, and some life could be evolving here, and then these biosignatures get carried up in the water column to the surface of the ice, where we could potentially take some observations and see whether there's anything going on. Now, so that's this is a dream world for people who work on hydrothermal vents, you know, because it gives them a great, you know, it's fascinating to think that this could be going on. Some of the work we've been doing is challenging this view of what's going on. So that's the big take-home message of my presentation. So, well, what do we know? This is my artist's impression of some of the things we know about. We know something about, we know the rotation rate of these. By the way, there are lots of icy moons. I'm really focusing on two. We know the rotation rate, we know the radius of the moon. We have some knowledge, particularly for Enceladus, about the depth of the ocean. We know something about, again on Enceladus, something about the ice geometry. It's thick near the equator, thin over the pole. And we have some constraints on the flux of energy going through the system. And that's based on knowing the surface temperature here, knowing the thickness, and making some assumption about the diffusion rate through ice. I don't know what we know about that. How heat would be transferred through such very thick layers of ice. But we can put some numbers in and get some constraints. It's about 20, 30 gigawatts, we think. And then the other thing and then this, oh, I should say something more. We probably know that Enceladus is fresher than Europa. So we know something about the salinity of Europa because it distorts the magnetic field. So you've got a magnetic field, the moon's moving through the magnetic field, and it distorts the magnetic field because it's a good conductor. So we think the salinity of Enceladus is quite high. The salinity of Europa is quite high. The salinity of Enceladus might be quite low. We have got a point measurement of the plume on the south, over the South Pole, and We do also know something about the equation of state of water. We know a lot about that if we knew what the oceans were made up of. And ice is going to move from thick to thin. So where the ice is thick, it's going to slump over to where it's thin. So it's going to melt. The ice is going to melt over the poles. Where it melts, it's going to be fresher than where, and we have to form ice over the equator. So when ice, which is made up of fresh water, forms, you squeeze the salty water out, so it's salty. So the equatorial oceans are likely to be salty, the polar oceans fresh. And there's also the fact that the freezing point of water is depressed at great pressures. So if the water's freezing at 30 kilometers depth here, it's going to be colder than if it's freezing at the poles. So we expect there to be cold, salty water at the surface at the equator, and warm and fresh over the poles. And that's going to drive some ocean circulation. And you can imagine there's this libration going on, this wobbling, generating mixing, and these boundary conditions are going to get mixed down into the interior, and we're going to generate a circulation. Or heat issuing from below is going to generate a circulation. I always like to root these things in something tangible. I can't really operate otherwise. So the melting, particularly when you're doing numerical experiments where you can just get into a numerical world. And when I first came to MIT, I was deep into thinking about deep convection in the ocean. And deep convection in the ocean is interesting for a number of ways, like in the Labrador Sea or in the Western Mediterranean, when you get mistrals blowing off the coast of France over the Med, it generates deep convection. Now, if you're a parcel of fluid near the surface of the ocean in the Labrador Sea, and you get cooled, you sink to great depth, and it takes maybe a day to get down to 2 kilometers. So convection and a day is of the same order of, it has the same timescale as the rotation rate of the Earth. So deep ocean convection is actually affected by Earth's rotation. If you think about convection in the atmosphere, a parcel of moist, buoyant air in the tropics makes its way to the tropopause in deep cumulonimbus convection in a few tens of minutes on a timescale which is much less than the rotation rate. So atmospheric convection doesn't know that the Earth's rotating, whereas ocean convection does. And I believe that convection on these icy moons knows a lot about convection. So this is a lab experiment that we did with Jack Whitehead, who is now emeritus professor down in Woods Hole. And so what you do is you get in one of these 8 millimeter ice, 8 millimeter canisters, film canisters. You dye the water, freeze them, and then you float them on the top of a tank, a rotating tank of water, and the ice disk melts and generates convection as it comes down from the top. So if you have a bird's eye view of this, these do look a bit grainy. They were taken many years ago, but we should do some new experiments. Here, can you see that this is the ice disk which is melting, and these are the plumes coming down, and they're really affected by the rotation rate of the system. And then if you flip it over, so I'm now thinking about Enceladus, right? So you've got a hydrothermal activity down below, and you're generating heating and that water is coming up. Well, what are the non-dimensional parameters here? So one of the things we find is that we get that the fluid parcels tend to align themselves parallel to the rotation vector, and we get this plumy convection. These are known as Taylor columns after G.I. Taylor, who began to study these in England in the 1920s. He was looking at rotating fluid experiments in the 1920s, and there's a buoyancy flux coming up from the bottom, which is related to the rate at which the ice disk is melting. The buoyancy flux has units of velocity times gravity. So it's got units of meter squared second to the -3. I'm going to use a dimensional argument. So if I now assume that rotation matters, then if I let time go to 1 over f, where f is the Coriolis parameter, twice the rotation rate of the system, omega is the rotation rate of the container, then you can get a length scale by dividing that buoyancy by f cubed and taking the square root. You're going to get a length scale. That length scale we call L-ROT. We did a lot of work of this in the early 90s. This length scale is L-ROT. It's b over f cubed to the 1/2, 0. And the velocity scale that we see here is b over f to the 1/2. If I divide by f and then take the square root, I get a velocity scale. And so there's a non-dimensional number, which is the ratio of this rotational scale. That's the scale over which the fluid begins to realize that the system is rotating. L-ROT over h, where h is the depth, is a non-dimensional number. And we can call that this natural Rossby number. A Rossby number is a number which is telling us how important rotation is in the system. So the natural Rossby number is 1 over h, b over f cubed to the 1/2. And we can estimate what that number is for these icy moons because we know the heat flux, we know the depth, we know the rotation rate. So we can kind of put Enceladus and Europa in parameter space. And so what happens later is that the convection gets organized into these clumps, which we call cones. Cones, the disk breaks up and we get clumps of water on scales of these cones, and the cones scale like the square root of h times L-ROT, which is h times the square root of this non-dimensional number, the natural Rossby number. So we've got a non-dimensional number R0 star, and then the other one is a number measuring geometry, which is the radius of the depth of the disk divided by the depth. That's another non-dimensional number. So let's apply these to convection on icy moons. And this is taken from a paper that came out this year with Suyash Bire being the lead author. So here we have our moon rotating round. We're assuming it's got a depth h, a radius r, and a buoyancy flux coming up from below. And there's a natural Rossby number, which is L-ROT over h, and there's a geometrical parameter, which is the radius of the moon divided by r plus h. And r over eta for Enceladus is quite small. It's like 0.8. Whereas for the Earth, it's 0.999. You know, the radius of the Earth is 6,000 kilometers. The depth of the ocean is only 5 kilometers. So that eta is almost 1 for Earth's ocean, but it's much smaller. And so here we are in my two-dimensional parameter space, eta and R0 star. And this is where we think Europa and Enceladus are in this two-dimensional space. And we've carried out lots of numerical experiments, and in Suyash's paper, we report essentially on 9 experiments, these 9. And the philosophy is the same in many parts of computational science. You can't do direct numerical simulations of this body. What you do is you identify non-dimensional numbers, you set up, you explore numerically the parameter space that you can resolve, and then you extrapolate, assuming that the same laws apply. And I think that's a rational way of going forward. Now, there are Taylor columns in this system, but the glorious thing about it is that the Taylor columns line up parallel to rotation. So you get this a really interesting thing where the fluid, the angular momentum surfaces are parallel to omega, and obviously they're grazing the sphere of radius r. And these things are, this is called the tangent cylinder, which is really important for deep atmospheres such as the dynamics of Jupiter or these icy moons. So what we are doing, and this is the work that Ali Ramadan has done a lot on, is develop this piece of code in collaboration with the Julia lab at MIT. It's written in Julia, and it's running on CPUs and GPUs. It's called Oceananigans. I've been told that this is, we're not going to be taken seriously if we don't come up with a more serious name. But anyway, it's attracting people to this, and if there's anybody's interested, you can download this code and use it. This is part of I should mention, Ali Ramadan and Greg Wagner are the kind of architects of this piece of software. They put a huge amount of effort into it. And it's part of the Klima project that you may have heard Raf Ferrari talking about. Raf was here a few moments ago, where a new climate model is being developed from the ground up. We at MIT are focusing on the ocean, and there's a group at Caltech funding, working on the atmosphere. It's funded by the Schmidt Foundation, and we are coupling these two pieces, these atmosphere and ocean ice together to develop this climate model. Now, what I'm doing here is leveraging that work to apply it to this other problem. I should also mention Alan Edelman and the Julia lab, who've been hugely helpful in getting these models going. So let me begin to show you some of the results. So this is a kind of reference solution where we take our model, put it into this kind of spherical, quasi-spherical system. So here's the equator going to the North Pole and the South Pole, and this is the temperature field at some point in the integration. And this is the zonal velocity. So this is the velocity along a latitude circle. And you can see that these columns are forming, these columnar structures. And those of you who know about, say, the circulation of Jupiter, Jupiter comprises lots of zonal jets moving in opposite directions. And we think that the circulation on Enceladus and Europa might echo some of the things that we're seeing on Jupiter. Now, what we do to present the results is show the results in a Cartesian way. So there's a coordinate y going from the equator to the North Pole and from the equator to the South Pole, and then z, which is pointing radially outwards, goes upwards. And then this tangent cylinder gets mapped onto this parabola. It's not exactly a parabola, but and then so I'm going to show you lots of solutions like this. So that solution looks like this, and what we see is the convection coming up, and it knows a lot about rotation, and the convective plumes align themselves parallel to the rotation vector. But in this presentation, they are moving along these lines, which are tilted. Now, outside the tangent cylinder, i.e. over here, corresponds to this part of the fluid, which is the equatorial part, and inside the tangent cylinder is here. And here we have these zonal jets, where we get multiple jets that we can think about what sets the velocity scale, the space scale, etc. And these kind of equatorial rolls that are occurring here, where you've got fluid spinning around in this direction. There's a marvelous literature that was started by Bussy in the 1970s, who anticipated these structures theoretically for deep atmospheres. So I'm going to show you some, just to give you a feel for the phenomenology of the solutions. I'm going to show you some what it looks like. These are running on GPUs really fast, and this is the rotation period. This is showing you the velocity, the zonal velocity field. This is the temperature field. So we turn on the heat, and there's this fire coming up from below. We're generating these rolls in the tropics, and there's lots of plumy convection coming up, but very much confined by the constrained by Earth's by the rotation of the moon. So the fluid dynamics, we get very excited by this kind of this fluid dynamics. There's lots of things we can do about it. Let me show you another view of this. This is looking down from the top, halfway up the model. And so here's the equatorial region. This is the polar region. And this is the vertical velocity. And you can see these rolls. So in the red regions, the water is rising, and in the blue regions, it's sinking. So we get these rolls in the tropics, and we get these beautiful zonal jets where the water's moving east-west. And there's an inverse cascade where the plumy convection energizes the larger scale flow. The cascade gets arrested to form these zonal jets. The dynamics of these things is understood in a generic way. Lots of marvelous work by Peter Rines, for example, in the 1970s on, these are called Rines jets, or can be called Rines, and they are fundamental to the kind of structures that we get out of that we see on Jupiter. Notice that the convection is plumy here. It's plumy inside the tangent cylinder and rolly within the tangent cylinder. Sorry, I should have said it the other way around. We've got rolls outside the tangent cylinder, plumy convection inside the tangent cylinder. Here's our sequence of 9 experiments. Many were done in this parameter regime, and remember Enceladus and Europa around here. This is the zonal flow. So you get a whole zoo of solutions. And I wanted to show you these calculations that Annika helped us do. So if you I've never understood this, but on these GPUs, you can release millions and millions and millions of particles and track them very easily. And here we have some particles which are being released at the bottom. Imagine that there's a little element of life on one of these particles and it's trying to make its way up to the surface. We want to know what the transit timescale is. And so what Annika did, working with Suyash, is to look at the timescale that it takes for a fluid parcel to go from the bottom to the top. So how long you can plot a PDF of the transit times, and you can develop some theory to try and understand that. So we have various scaling laws. I reviewed that in a generic way, in a brief way. This is the horizontal speed divided by, this is the typical horizontal speeds that we see in the model, divided by f times h. F has units of 1/time, so divided by the this velocity measure. And we can make predictions about how this depends on R naught star. R naught star is small here, large over here. The Earth's ocean is around here. Earth's atmosphere is around here. Enceladus is down here, off the board a bit. So these are our theoretical predictions against the predictions from the from our scaling laws. This is the vertical speed. This is the aspect ratio, the scale of those rolls that I was showing you, to give us a feel for the kind of and this is these are Annika's vertical transit times. So you can see that as we go from towards low natural Rossby number, the transit time in number of rotation periods gets to 10,000. So we're talking about hundreds of years, decades to hundreds of years for a fluid parcel to make its way up to the top. Now, so that's why we think short transit times, which have been speculated, which have been, people have published papers saying that the transit time could be a few weeks or days or weeks. We don't, these results suggest that that's unlikely to be the case. The equation of state of seawater, how much longer do we have? Not much longer. I have to say something about this because it's important. So you know that if you go to Maine in the winter time and you've got these freshwater lakes and there's ice forming on the lake. So the reason that is that if you've got fresh water, this is fresh water, the blue line, if you cool it, the water actually gets lighter. So if you cool fresh water near its freezing point, it doesn't sink, it actually gets lighter. And so the water stays up near the surface and gets colder and colder and freezes over. Whereas if you had salty water, if you cool salty water, it actually gets denser, which is one's physical intuition, and the water sinks. So if Enceladus was very fresh and you warmed it at the bottom, you would actually create heavy water, and you wouldn't get plumy convection at all. So so there's another effect that I've sketched this out here. This is the freezing point, these dots here, that there's a suppression of the freezing point of water at great depth. So the dotted line is shallow, the continuous line is deep. So if the water freezes at a colder temperature, if it's deep, than if it's at high pressure than if it's at low pressure. That's really important. So for example, imagine that you had Enceladus with a thick layer of ice here and a thin layer of ice here. it would be cold under the thick ice, but warm under the thin ice. And so if the water's very salty, cold water sinks and you get an overturning circulation like this. If it's very fresh, it's the warm water which sinks and you get a circulation moving in the opposite direction. And this has been studied by Wang-Ying Kang in several papers which are now out. Wang-Ying Kang's exploration of the ocean circulation on Enceladus at different temperatures, assuming different salinities. Both of these circulations carry energy from the poles towards the equator. So what's the ocean's trying to do is there's heat going out. The ocean's trying to is carrying energy towards the equator and actually melting, trying to flatten out ice thickness variations. We think on Europa, the ocean may keep the ice variations fairly flat, whereas on Enceladus, that might not be the case. There's also a salt-driven circulation. Where water's salty, it's heavy. And so you get an overturning circulation driven by salt. And the ocean carries the fresh water this way, and there's a freshwater transport in the ice. Okay, so I'm going to, in the interest of time, I'm going to finish here. We can look at hydrothermal plumes in salty oceans, and this is work that Tushar Mittal has been doing. And on the left, we have a salty ocean, and hydrothermal activity is pushing particles up in the vertical. On the right, we've got a fresh ocean, and that generates density currents that just move away. So if Enceladus is like this, it's going to be hard to get information, much harder to get information up vertically. Don't have time to talk about this. Okay, so just to finish off with my conclusions. So ocean circulation of Enceladus and Europa will be strongly constrained by rotation and geometry of the tangent cylinder. This natural Rossby number is very small on these moons. And there are going to be rolly dynamics, rolls in the tropics, and plumy convection over the poles. We expect zonal jets to be ubiquitous. If you energize this system, you're going to generate zonal jets. Vertical transit times will be long, decades rather than days, and the geochemists are very interested in this because they have geochemical models which can also put constraints on transit times. The circulation will be driven from the top through the interaction with ice, from the bottom through hydrothermal activity. This current paradigm may be misleading. I think it is misleading. I don't think Enceladus is likely to look like this. It's going to be very hard to get deep signatures up to the surface. There's going to be a lot of lateral mixing going on. It's more, we're going to excite these zonal modes, which are strongly affected by rotation. And many of the details will depend on the assumed salinity of the ocean. Okay, more details. So there is this paper by Suyash Bire, and there's a paper by Wang-Ying Kang on the role of salinity. Many other papers coming out or about to hit the journals. And if you want to look at some of these things, you can find them on my website. Thank you very much.
Okay, so now the floor is open for questions. First, we can take questions that you have here. I actually have one question, and then we will check the chat. So before that, any questions here? Or maybe can I start with the first one? So you mentioned the experiments that you do, the actual natural Rossby number is very low. And I was thinking, so what is the constraint in the lab to really reach such a low Rossby numbers? You just need to rotate very fast your experiment.
Well, yeah. So there are laboratory analogs that you can carry out. We have a fluids lab over in Building 54, the tall building with the radar on the top. And there are lots of rotating turntables. So if you spin a tank around of about 1 meter in scale with a period of 10 seconds, the typical Rossby numbers you'll get in that tank are 0.1, 0.01, you know. So you doing self-gravitating spherical calculations, you need magnets and magnetic fluids to kind of glue the fluid on. That's a much harder thing, but you can do flat Earth or flat moon calculations rather well in the lab.
Rossby number are 10 to the -6, or is that the ones that you will really get there?
Yeah, you just need small, and then you extrapolate down. It would be really hard to do direct numerical simulations. It would be impossible to do.
Yeah. So that when you have your scaling laws, you have two regimes as a function of, like, Rossby number 10 to the -2, you have different scaling laws. The way you were scaling the parameter. Is that a prediction from the theory? Because it was very difficult to see from the data you have that actually the scaling will change, but seems to be very sharp, like with your prediction where you have Rossby number.
It's a transition. So it's not, you know, if the Rossby number is 10 to the -1, it's going to be gripped by rotation. If it's 10, it's not. So there is a transition between about 10 to the -2, 1 or 2, and 10. Atmospheric convection has a Rossby number of about 10. Doesn't really bother it. Convective complexes know about rotation, so they have a corporate awareness of rotation, but the individual elements are probably not aware of rotation. That's not true in the ocean. Rossby numbers much smaller there.
Okay. Yeah. Yes.
Nice talk. As we know that in the Earth's ocean, the mesoscale eddies is important to drive the zonal jets, like through the buoyancy flux and momentum flux. I wonder how important is those eddies in the icy moon?
Yeah, that's a very good question. And we didn't have time to talk about that, but I could say something about it. So if one has an upper boundary where you've got temperature and salinity variations, then you've got density gradients at the upper boundary. And that's exactly what we have, density gradients in the Earth's atmosphere and the ocean. So the polar oceans are cold and the equatorial oceans are warm. So there are density gradients. Those density gradients drive other kind of instabilities, such as baroclinic instability or slantwise kind of convection. And this is one of the big things that we're studying now. Wang Ying has been working on this. Yi Zhao Zhang is working on it, where we look at diffusing down into the interior this boundary condition, which has got horizontal temperature gradients in it, and you generate baroclinic instability. So Enceladus and Europa will have baroclinic instability going. Baroclinic instability is the theory of weather systems. Synoptic systems in Earth's atmosphere are baroclinically unstable. They are baroclinic eddies, and we will have analogs of those on these icy moons.
Again, thank you for the talk. I'm well outside of this domain, so please forgive if this is a very naive question, but you've mentioned that it's very hard to take direct measurements of this system. You know, it's obviously quite far away and well under a sheet of ice. So I'm curious, what would the quote unquote like dream data set be that would really reveal maybe the truth here, or really help you develop these models further? You know, what probe would you need to send where to get what data?
Well, I think what the Europa Clipper mission is looking at gravity measurements, topography measurements, spectroscopy. You can from the spectroscopic properties of the surface of Europa, you might be able to figure out, is it salty or not? So it's mainly the physics and the mechanical properties, the thickness of the ice, those kind of things. If we could get up to Enceladus, which is not going to happen certainly in my lifetime, maybe in yours, although we'd have to, you know, if we got to Enceladus, I think you could imagine getting over to the south pole of Enceladus, getting something down into the ice water regions and beginning to make some measurements. But good question. And one of the things that we always like to do is to hook it back to some observable quantity. Otherwise it becomes a navel gazing kind of exercise. And there are whole teams of NASA engineers who spend their days thinking about what can we measure.
Okay, I think that we are already over time. So thanks a lot, John, for the talk. And thanks
very
everyone
much
for joining us. And then we'll have more seminars next semester. So thanks. Thank you again. Okay.